Okay, I would like to do one. The first one, we're gonna go, how about we'll go through just one problem, and try to flesh out everything. First, what does it say?
Want me to just go to the first one?
Yeah, go ahead.
Target received power, determine the single pulse received power level from a target for a referencing having following characteristics. Transmitted 100 kilowatt peak, frequency 9.4 gigahertz, antenna gain 32 dB, target RCS 0 dB,
Meter squared.
and then target range 50 kilometers.
All right. I'll add some to this in a second. This is a standard kind of problem. Now, it's based, this one you should be able to do without anything I put on the board last time. This is right from Whitmer's book. So, receive power, the way I like to do it, I start with the transmit power, right? Then divide that, where is that, over 4 pi r squared. R is 0. Now, that would be the isotropic power radiated. Everybody with me on this? Okay, we're going to walk through the whole 9 yards because this is your final example. All right, the minute I multiply it by the gain, but do I multiply it by 32, class? Over here? No, that's dB, isn't it? It would be 10 to the 3.2. I want to put down, right, because when we talk about dB, and this is a common mistake. dB, if gain is in dB, that's 10 times the log of the actual gain. So if you want the actual gain, you take 10 to the gain in dB divided by, it's going to be gain in dB divided by 10, right, to the 10th power. And that would be the linear gain that goes in that equation. Y'all follow me? Now we can take 10 times the log of that. We can get everything in terms of dB. But this is, I'm trying to just give you one formula to work. Y'all with me? All right, so this would be the power density right here before the target. This is the target. And the RCS, usually given as sigma, is 0 dB meters squared. What is that? Well, when we talk about dB square meters, anytime you talk about power-related quantities, when you think about that, the radar cross-section is meters squared. We're going to multiply the incident power density by the radar cross-section. This is power. Everybody with me? So that means that in terms of dB, it's 10 times the log of this was equal to 0, correct? That's 0 dB meters squared. If we divide that by 10, we still get 0, so sigma is 10 to the 0th power, or 1 meter squared. Y'all follow me? If I don't work through this problem and put something like this in a file, I usually get errors with dB, either here or with the gain or on both. Y'all with me? All right. So this is the power density incident right here. Now I'm going to multiply it by the RCS. And these are questions I ask. I'm going to tell you. I'll ask, what is the power density incident on the target? Then I'll ask the total power reflected by the target. So I'll call it P reflected, would just be equal to transmitted power over 4 pi r squared times, in this case, 10 to the 3.2 times sigma or times 1. Y'all agree with that? Right? That's the total power reflected. Sigma is the RCS in meters squared. This would be a power density without that. Power density is in watts per meter squared. This would be in watts. You all agree? I asked for this. Here's another quantity I asked for. We'll fill them in a second. I asked for the E field or the H field strength right here. How do we get that in? If I want the electric field or the magnetic field strength right here, incident on target, how do you get it? Well, what is, do we have a propagating wave? Assume it's in, right? Y'all remember that average power, you have to know this stuff. Average power for a waveform at a constant frequency, this is the average power, is 1/2 the magnitude of E squared divided by A0, or it's equal to 1/2 times what? Eta times the magnitude of H squared. Y'all with me on that? So if we want E, what do? We say the E field incident right here. E field incident on the target would be equal to what? 2 times eta naught times the actual P average, or P, I'll just put it in here, times P transmitted over 4 pi r squared times 10 to the 3.2 power. It would be the square root of, this is the power density on target. I'm not done with this equation, but I'm just getting other quantities. Y'all with me? If you had the E field, how do you get the H field, class? Just in case I asked, H incident would be on the target. Class? Magnitude would just be what? 2, well, incident, well, you could do it that way, but if we got this, isn't the incident electric field divided by eta naught the magnitude of the H field? I'm trying to show you shortcuts. Y'all with me? So bang, final exam problem. I want the power density on the target. I want the E field on the target. I want the H field. There we go. This is the total reflected power, right? Getting back to here, so I multiply this by sigma. That's the total reflected power density, correct? What do we do next? Well, we divide that by 4 pi r squared, because now all that reflected power is going to start dying off as the surface area. So we divide this again by 1 over 4 pi r squared. That's the power density back here, right? This would be the average power density, I'll call it P-ab incident, right here. Do you agree with me? Now, you can calculate that P incident, right? I can also find the incident electric field back at the antenna, reflected, right? Just take that, multiply it by 2, multiply it by eta naught, and take the square root. You all agree? And then I can take that E field divided by eta naught to find H. Agreed, class? But I don't want to do that. That's the incident power density right here. Now what I want to do is find the amount of power grabbed. Correct, class? So how much power is caught? I need to multiply this by the aperture. Right? In case you don't remember, the aperture is equal to lambda squared over 4 pi times the gain of the receiving antenna. In this case, they're both the same. Agreed, class? So the receiving and the transmitting have the same gain. So up here, what we do if we want the power received, we just take this whole thing and we multiply it by lambda squared over 4 pi, and then we take the gain again, which is 10.32. The reason I put 10.32 down here is so you know it's not 32. People will put down, I promise you they'll put down 32. Here, sigma is 1, isn't it, class? Not 0, 1. Okay, so that's the received power. Now I'm not done with it. Okay? If I go ahead, I'm going to add something. So suppose I say the waveform looks like this. Suppose I draw out a waveform. And I said this is the transmitting power. Yeah, I might as well call this the transmitting power density. Now let me do this. Let me take a look. Say this is going to be 1 over 1,000 And this is going to be 1 over 10,000 seconds. This is going to be time in seconds, okay? So this is the actual transmitted power waveform. Now, I tell you it's 100 kW peak, right? Not exactly true, is it? Really what happens is that's the average power that's being transmitted right here would be 100 kW. If you actually remember back in the day when we had power engineering, if you looked at a power waveform, it does this, right? Where this would actually be the peak power, right? And then this would be the average power. Do y'all remember that? Correct, class? Now, you remember with VRMS, if VRMS was what? I mean, V peak was VRMS times square root of 2. Do y'all remember that? Or VRMS is V peak divided by square root of 2. Do y'all remember that? Well, if you think about that, if you have VRMS times VRMS squared divided by the impedance or the resistance, you have the average power, right? Well, the peak power would be what? 2 times that, wouldn't it? So that means the actual peak power is this. It's going to be twice the average power during that transit. But usually we just talk about the average power because it's the effective power. We don't worry about the absolute peak in the waveform when this thing's on. Remember, this thing's actually doing this. You know what I mean, everybody? Just worry about the peak. They call it P average peak during that cycle when it's on. With me? I'm not going to ask you for the peak of the power when it's on, but you need to at least appreciate that. So if this is the waveform right here, where this is 10 to the minus 4 seconds, and this is 10 to the minus 3 seconds, and it repeats itself, then what is the actual average power transmitted? That's the peak power. What would the average power? Now by average, I mean the average power over the waveform, because it's periodic forever. How do you get average power always? Well, you take peak power, right? And you multiply it by tau over T, don't you? What's the name for tau over T? Another name that you're familiar with?
Duty
cycle, right? So what's the duty cycle for this waveform? Take a look. 1/10. So the average power transmitted would be simply 10 kilowatts. Agreed, everyone? Not done. You with me so far? If you like, I can put this instead of 1 over 10,000, I can make it 10 to the minus 4 seconds. So make this 10 to the minus 4 seconds, and make this 10 to the minus 3 seconds. Want to show you? Now I'm not done. But you understand we can feel it. By the way, how about you guys give me some of this stuff? What's the wavelength? It's going to be a C over F, right? Or C over F is equal to lambda. You can give me that value, anyone. 3 times 10 to the 8th divided by 9.4 times 10 to the 9th, right? What do you get for that?
0.032.
Meters, all right. All right, now how about P received? Might as well fill these in. Transmitted power times 10 to the 3.2. 1,000 times 10 to the 0.2, which I don't know what that's. Anyone? I mean, can you do this? I can get rid of C as 1, so I just can get rid of this. And R is 50 km. I'll write down the equation that's most generally acceptable for this. This is the one you're going to remember probably. It's transmitted power times gain at transmitter, gain at receiver, lambda squared times sigma over 4 pi cubed r to the 4th. That'll get you there, right? That's the condensed form. That's taking all the constants and putting them together. Here, gain receiver, gain transmitter are the same. They're both 10 to the 3.2, or really what, 10 to the 6.4, correct?
I got 1.03
For this whole
nano. Yeah, 10 to the minus 9.
1 point, what did you say?
0.3.
Times 10 to the minus 9
Yes.
watts. Anybody confirm that? I don't know about this. Not really.
I'm not sure.
Key thing is making sure the gains are. So you have to take 10 to 3.2 times 10 to 3.2. So that's 10 to the 6.4, right? Times the transmit power over 4 pi cubed, r to the fourth, lambda, which is 0.032 and squared times 1. Sigma's 1. What do you get? Do you have it there?
I don't know my calculator there.
Do you have MATLAB or any you don't have to do it. When I do all my calculations on a laptop, I use MathCAD usually because it's what you see, and I can do it faster than a calculator. The nice thing is I can edit anything too. Just for tips, if you ever want to do something where you need very pretty formulas to put in papers, and you don't want to do the derivatives by hand or the integration by hand, use Mathematica. It'll give you a LaTeX form, the output of either integration, differentiation. It's amazing. If you want to use just something where you're not doing wild matrix calculations to get answers quickly, MathCAD is the best. PCT, MathCAD, I think it's called. Unbelievable. If you want hardcore matrix processing where you got a lot of things you want to write code you can port to C, use MATLAB or use Octave or use Python. But MATLAB's got all the toolboxes. It's amazing. So what'd you get for this thing? Anybody confirm that? Is it right or wrong?
I got the phone number, but I'm not sure.
All right, what'd you get?
I got 2.07 times 10 to the negative 14.
P
That's what I got.
okay, so that's 100K for PT or no?
Yeah.
Oh, okay, cool.
Which is 10 to the
Yeah, I'm not
fifth.
sure. Okay.
So you got 10 to the fifth transmitted. We can estimate this. We got 10 to the fifth here, right? It's times these two gains, which is 10 to the 6.4, right? So that's going to be 10 to the 11.4, right? So I got 10 to the 11.4 times lambda, and lambda, that's 3.2 times 10 to the minus 2. So it's 10 to the 9.4, roughly, and times 3. 3 times 1, 3 times 10 to the 9.4 over r to the fourth, 50. So it's 5 times 10 to the fourth, 10 to the fourth to the fourth, 16th, right? And I'm going to start thinking I better just default to check. Anybody come and check that again?
I've got that second number.
Okay.
2.0. Let's see if that's right, but I'm going to warn you about this. This simple calculation people take for granted, people will make mistakes on, you get it wrong. On a final exam with a problem like this, there's no partial credit for this thing. I'll ask you for this. I'll ask you for P reflected. You've got to make sure you get that number right. You got me on that because it's so straightforward and so easy. It's not. This is not a complicated thing where you're doing the integration of some function. Everybody got that? Okay, now I'm going to assume that's right, but I don't know. You got that right? You got it too? Anybody else? You got it? I got 4 people. I'm going to guess the second one's right. Okay. Now, give me this. If I multiply this times 1, it's the same thing, right? So the reflected power is 2.07 times 10 to the minus 14, and that would be watts, right? What's the incident power? I mean, incident E field on the target, take this times 2 times 120 pi and take the square root of it. I'm just curious. Oh, I'm sorry, that's not correct. I'm sorry, this is the reflected power would just be this quantity here. Can you give me that? Well, yeah, that'd be a reflected power. Just take 50 times 10 to the third times 10 to the 3.2 over 4 pi divided by r squared, and r is 50 km, 50 times 10 to the third squared. What do you get for this part? You'll thank me for having a calculator out. Believe it or not, people make so many mistakes typing in numbers.
I got 2.5 times 10 to the negative 6.
Anybody else? This would be once. Anybody? You got a different number, just tell me.
Yeah, I think it might. Wait, hang on.
Same number or different?
Different.
Yeah.
What did you get?
I got 5.45 times 10 to the negative 3.
Yeah, I got that too, actually. I re-entered it and I got that.
You recalculated
Yeah.
that? Okay, I'm gonna bet that's right. All right, what's the E field? Well, this happens to be the same thing as the incident power density because the radar cross section is 1, right? So the E field, you take that number and multiply it by 1. 289 and take the square root. You all agree with that? What did you get for this, anybody? Just take that number times 125 times 2, 240 pi, times that number and take the square root.
Okay, I got 1.95.
For E,
Yes.
1.95?
Yeah.
No, so this is volts per meter?
1.9503. Yeah, it's not raised to anything.
All right. That's actually surprising, but actually, let's see. That squared, call it 2 squared, is 4 divided by 2 is 2 divided by 125 is 1 over 65. Yeah, okay, all right. Yeah, I'm buying it. That sounds about right. All right, what's the H field? Take 1, that over, it's roughly what? 1 over about
I got
60 pi.
that's 8 and not on the bottom, right?
Yeah.
Okay, I got 5.17 times 10 to the minus 3.
And that would be amps per meter or 5.17 milliamps per meter. Anybody else get that? Okay, good. I'm glad we're getting that. All right, now we got the average power. Next thing we want to make sure everybody gets is what is the maximum non-ambiguous range? That was something I asked. How do we get that? Anybody remember? Well, remember a radar pulse goes which way? It goes out and comes back, right? And the thing that limits the ambiguous range is that when you send this pulse out, it has to return before it hits here, correct? You all with me? So the way I always tell people to think about it, well, what would the distance traveled be by the speed of light over 10 to the minus 30 seconds? Call this capital T, it would be T times C. That's the distance. What distance does that correspond to? Twice the maximum ambiguous range, right? Because it goes out and back. So RU times 2 would be C tau, or the maximum unambiguous range would be C times T over 2, right? And what is that? 10 to the minus third, okay, times 3 times 10 to the 8th. This is going to be 3 times 10 to the 5th, right? Divided by 2 would be 1.5 times 10 to the 5th, or it would be what? 150 kilometers. Do you agree with that?
I got that.
How many do? It's 150 kilometers, isn't it, class? In the back, Lydia? Now, what's the maximum unambiguous range? This is where it's not, or excuse me, what's the range resolution? How close can you see 2 targets that are radially separated? Remember how to get that?
What is that going to be, the last one?
This is the unambiguous range.
Yeah. What, And what's the one you just said?
This is called the range resolution.
Range rate.
Right. Remember how to get range resolution? Remember I said there's a pulse with a certain width going out, strikes the target, starts reflecting, right? There's another target separates, same pulse hits it, starts reflecting. You find out, in order to get no overlap, it's similar to Nyquist and what he's doing, is to take C, right, times, now it's tau over 2. Now, what's nice is this, look. The relationship between T and tau is the duty cycle, isn't it? So if you know this, if you want this, you just take that range, unambiguous range, and multiply it by the duty cycle. So it's going to be 1/10 of that, or 15, right, kilometers. Now here's something just to tip. That's a 10% duty cycle. A range resolution of 15 kilometers is not good. All right, unless you're talking about long-range navigational radar, where they really don't care about that. They care more, yeah.
How do we know we have 10% duty cycle?
Well, remember here, this is on for 10 to the minus 4 seconds. This is 10 to the minus 3, right? So the ratio of the on time, tau, which is 10 to the minus 4, divided by the actual pulse repetition interval, or T, 10 to the minus 3 is 10 to the minus 1, or 10.1, right?
So how do we get 10 to the negative 3, 10 to the negative 4?
I put them up there.
Okay, so you gave us those.
I just arbitrarily, that's not in the problem statement. I
Okay.
decided that that's what it is. I'll change that on the file. I have seen this on exams before. People get into this mode with a burnout, they've been studying, then they take stimulants and stuff. They come in there and they remember a problem, and in that problem was this value. I'll put this value down. And they're not thinking, they're reacting, and they get everything wrong. They'll take things out of their memory and put it on paper, and it's completely wrong. Please make sure you think through the problem. That's how you, yeah.
Can you explain again what the range resolution is?
Sure. If you have two targets, say this is my radar. And I have two targets, one here, one here. The range resolution is the minimal distance you can see two different targets. Otherwise, they appear as one. That's the thing. It's just it's the reality. And in the way you get better range resolution for delta R to decrease, you have a smaller tau top. Now, there's a lot to be said here, because the smaller tau is for a given capital P, the less average power. And the less average power, the higher the signal to noise ratio. You all understand that? Signal to noise, the noise power you're going to see in a second, that's equal to K, which is Boltzmann's constant, 1.38 times 10 to the minus 23rd joules per kilogram degree Kelvin or something. But it's 1.38 times 10 to the minus third times the bandwidth times the temperature in degrees Kelvin times something called the noise figure, which is really a fudge factor. That's the noise power in an amplifier. Did you all have noise power when you had your analog? You did? Well, you know, it's always proportional to the bandwidth of the amplifier and the operating temperature. You all remember those things? That's the only thing you have to know. With amplifiers, the hotter they are, the worse they are. You get shot noise, you get all these different types of noises. And the wider the bandwidth, the more noise. Let's just remember that. Now, are you good with this class? Everything? I think we got it all. I mean, those questions will appear on file. I can't be more clear. Something else, William mentioned that he took a poll, and the results of the poll said you wanted a review session Wednesday, right? I'm going to target Wednesday at 1 o'clock in the afternoon, but I got to check my calendar on that. And William, why don't you send me a follow-up to make sure I get this right? And if I can, I'll do it at 1, unless you prefer a different time. I can do it earlier for some, but I don't know when you have your final. That's the problem. I don't know when you have finals. So if you can get me a time when everybody's free.
I'll send another poll.
then I'm fine. I mean, but get it to me today or tomorrow, because here's what happens in my life. All right, I am not administration, I'm not the president or anything. So what happens is this, they stick appointments in my calendar, whether I like it or not, but they don't always do it 2 or 3 weeks in advance. It may come up on short notice. I got a doctor's appointment tomorrow, I'm just thinking all the things that I put on my calendar, I didn't put that on. I've tried to put in things on my calendar so they don't, but sometimes they just overwrite them. It's like, change that, because this is more important. And in fact, they have a right to do that. They pay me, they can do what they want with my time. I have my time, and I'm salaried, so it doesn't matter if it's 10 at night or 8 to 5. And that's just the reality. But anyway, they try to be very fair about it. Now I want to get into something called signal to noise, which is so important. Did you cover signal to noise in your courses on analog or digital design? You did? Signal to noise is critical. And the reason is because these signals, when we receive power, they're so small. I mean, the power density you're getting back from radar signals is super small. We actually don't just get one pulse. We get a whole series of pulses back. We do what's called coherent processing. That means we literally, I'll show you what that is in a second, but we know the signal we send. Right? So what we'll do when we get a received signal, think of it mentally this way. You take a picture of the signal you sent. And the signal you receive will have noise on it. But what you do is add it to the signal you sent, and we actually involve it. And what happens is the noise from more and more pulses doesn't add. It's wideband noise. But the average power does, and that means the signal noise goes up. I'll try to explain this. First, we talk about noise power. All right. Noise power in general. For almost any amplifier, any device that's electronic, it's equal to K. I'll give you K, it's Boltzmann's constant, times the temperature in degrees Kelvin. I'm going to put degrees K, well, I'll put K here. It's got to be in Kelvin. And it's times the bandwidth of the amplifier. I'll put down what these things are. Then it's times something called the noise figure. So K is equal to 1.38 approximately times 10 to the minus 23rd. And it's joules per degree Kelvin per second, I think. But don't worry about the units right now. Temperature. This is T is in temperature in degrees Kelvin. B is the bandwidth. And this is in hertz. I'll put down H, Z, F really in hertz. And F is the noise figure. Or I'm sorry, it's the noise figure. Noise figure, typically, it'll be 1 or less than 1. It might be 0.2, it might be 1, it might be 1.5, something like this. But this is how much noise power is. Thing to take from it is proportional to the bandwidth. The wider, I mean, this is the noise power. The wider the bandwidth, the more noise. This is nuanced. I believe this is true for any amplifier. Maybe not digital amplifiers because there might be other effects. But any normal analog wideband amplifier that's used for the power amplification of a signal. And that F is probably something that is measured for any amplifier. Take a note of the temperature. Temperature goes down to absolute zero, the noise power goes to absolute zero as well. Have you heard of cryo cooling with liquid helium things, amplifiers? The reason they do that is when that temperature goes way down, there's no noise. Now, the reason that's real important, it's in deep space stuff. When you're looking at distant stars and you're doing any type of data processing, the signals from some of these things are so, I mean, you think about optically, If you're in the microwave band, a lot of this stuff is deep space, it's astronomy, but it's done, it's really astrophysics. It's done in the microwave band. The signals are so very small. The only way they can really get something out of it that's meaningful is to use liquid helium, which is very expensive. All right. Now, when you talk about an amplifier, there's the SNR, which, I mean, not an amplifier, a radar unit. This is called the signal to noise ratio. It is an extremely important quantity. And what SNR is just what it says. It's the signal power received, usually the average power, but it doesn't have to be. It's the signal power received divided by the bandwidth, or divided by the noise power, P noise. Sorry. So that's the noise power, and I'll call it P sub n. That's the usual designation. I'm going to put down what it is, and this is going to be the peak signal to noise power. And I'm going to show you some interesting things. I'm not going to try to go too deep into this. I want to make sure I'm fine with that. I'm not going to stretch you on this one. I'm just trying to give you something. So if we take the signal power received, just think about it. We take transmitter power, right? Gain of transmitter, gain of receiver times lambda squared times sigma over 4 pi cubed r to the 4th. That's the signal power in watts. It's actually received back from transmit. Y'all with me? It's the peak power too. Now if we divide that by noise power, that's K times T degree Kelvin times bandwidth times the noise figure. That's the SNR. And by the way, this formula I just put up here is probably the most go-to formula for the beginning of any kind of radar, you might say discussion or analysis. They go to this equation. Now this is the best it gets for a single pulse. The average power will bring this down by the duty cycle. Remember that. So I'm going to start showing you some things that are done. Y'all with me on this one? If I ask for signal noise, what is the temperature, room temperature, basically, in degrees K? You remember? Back in the day when you had microelectronics, you remember there was KT over Q. It was what? That was 26 millivolts, right? Or, yeah, KT over Q. Q over KT is 1 over that, but 26 millivolts, that assumed a temperature, Boltzmann, that was Boltzmann constant, right? And the temperature was what, 270 to 290? Look up room temperature in Kelvin, see if I can. I know I see different things. I think it's 270, but I see 292.
It says 293.
293, is that 72 degrees?
Yeah.
I think the British used to. The British use 270 because it's outside there, the average temperature is like 40 degrees.
It's assuming 20 degrees Celsius.
What is it?
293, assuming 20 degrees Celsius.
Yeah.
Yeah, and that's room temperature, isn't it?
Yes.
I don't remember.
Yeah, a cold day would be 10 degrees Celsius.
Well, I mean, what's 72 degrees or 70 degrees? Say again?
I think about 20 Celsius.
20? Okay.
At 293.
293 for, use 290, all right, for room temperature. But you'll see different things, don't freak out about it. It doesn't matter. And I'll tell you what temperature, I'll give it in degrees Kelvin. I don't expect you to convert. But that said, I do expect you to understand that's the form. Now, here's the things we modify. First, bandwidth of an amplifier, B, it has to be this or the whole thing goes to pot. The bandwidth has to be equal to 1 over tau of the actual signal. Let me just show you something without going in. I'm not going to dive into this, get into the weeds. Do y'all remember back in the day when you took signals in the system, you had a function called a rector or pulse function. It was p sub tau of t from minus tau over 2 to tau over 2. You remember that one? Then you have the Fourier transform of it. Well, the Fourier transform of this was tau times the sinc of omega tau over 2. The sinc function is sine of x over x. So it would be sine of omega tau over 2 divided by omega tau over 2, right? Just hear me on this. Well, if we replace omega by f, that's 2 pi f, or this is pi tau. Right? And you remember, for that sinc function, this is a sine. When is the sine? This would be f. Pi times, sorry. It would be pi times tau times, my bad. Pi times tau times f, I'm sorry. All right. Now, when is the sinc function equal to 0? Well, think about the sine of x over x. So whenever the sine of x is 0, it's 0, but that's actually a relative maximum if we use L'Hopital's rule. The first 0 is when the argument of the sine function is equal to pi, right? After that. So if we set it equal to pi, you see the first frequency here is 1 over tau, right? And if we just took the magnitude of this and plotted it, we see this. And it would look the same way in this direction. And the reason they say bandwidth is from the actual center frequency to the first null is 1 over tau for an amplifier. Now, if you're going to use an amplifier to do this, you have to be able to cover this frequency. This one's down 13.45 dB. Typically, the amount of power out here becomes trivial. It's not like 93%, 94%. It's inside the first null. So that's where they get the actual bandwidth. Just in case you go out in the real world and people start talking about that, that's why they're talking about it. It's not the real bandwidth of waveform. I mean, that goes on for infinity, right? But the first to the first null, and that's what the amplifiers need to have. So when they start saying the bandwidth is 1 over tau, what they do is modify this. And now, that's 1 over tau, so on top it just becomes tau, right? You know, now take a look at this for a second. That's temperature, that's tau. Hear me on this. I want to just, this last thing I want to do. Now, what if I didn't want peak power but average power? Well, I want to put in average power. And I know peak power times tau over T is actually equal to average power, isn't it? That would be the average power during a cycle. Do you all agree with that? Over a period. Well, that average power, if I multiply this times T, right? These two is equal to this, so I can take tau times P transmitted and replace it by the average power times the pulse repetition interval. So that becomes P av. Don't worry about this, I'm not going to freak out. Remember, it's going to be, here's what I'm getting at. This is going to be P av times T. Now this, better put down PRI here, pulse repetition interval, so you don't confuse it with T's temperature here. You with me? Yeah.
I thought PT was already the total average power density.
Now PT is the power during the on time of the cycle. It's like, if you look at transmitted power versus time, it does this. Right, it's true that is an average of the peak value there, but we just call it peak. So this PT, this value right here is called PT right there. That's the peak transmitted power. Even though it's averaged over that interval, it's the effective power during this time right here. The average power would be that times the duty cycle, right? So if you take PT, the transmitted power times tau over capital T, am I over?
No, I'm sorry, I got Ryan, I got Amy. I'm sorry.
That's equal to the, if I divide this by T, right, then you get that, right? So if I multiply both sides by T, I get that. And T is just the period, or the PRI. So I put PRI in here. Now, here's the other thing I'm going to tell you. PRI is 1 over the pulse repetition frequency. This is just a little playing around. So I can put this as 1 and put this as PRF here. This is a very common form of the radar equation also. Now, I'm just going to say this so you don't get worried. The first equation I put on there has all the things you need to solve any problem I give you. The thing is, you might have to get average power from peak power and duty cycle. You may have to figure out what the duty cycle is from a waveform like I showed you. And in other words, you have to understand the basic stuff I showed you. And this would be the signal to noise bound. I'll give you a few problems on that. I'll give you the answers. So you're going to give me that whole information. And that's it. This course is over. I enjoyed it and I tried. Sorry if I missed it. Did I miss one day or not? I missed the day in my radar class. My car literally broke down in the middle of the street when I was driving up here. And we couldn't even, the cop and I were trying to move it. It's a 2010 Veritas. I learned something. This is a car where you can't shoot out of here without a battery. Right? And the alternator went dead. So now the battery loses charge, car dies. Can't take it out of park. We start wiggling the terminals on the battery. Finally, we got the thing out of park, and in neutral, we shoved it out of the way. And I missed the class because of that. That was an embarrassment. Yeah.
Do you still have quizzes upstairs from?
Yeah, come on up. If you need test quizzes, whatever you need from me.
Will the format of the final be fairly similar to the ones from past semesters? You don't, I guess, yeah, it's kind of broad.
I hate to say, because there's a problem. I know the finals are all up, right? And all my exams are up. But if you study those, you're not going to see this. Huh? I don't think I've ever put that on a phone.
Okay.
And not only that, you're going to see stuff. Somebody asked about EMAG 1 stuff too. I think it was linear. For EMAG 1, the only thing you need to do is an inductance problem and a capacitance problem. For instance, if I ask the inductance of a 2-wire line or capacitance of a cylindrical plate capacitor of a certain length, I'm not going to ask you wild, crazy things, all right? Just capacitance or inductance with me. And I may only ask one of them, so maybe one or the other. And the real reason is you have EMAG 1, but we're supposed to give you 1 problem or 2 problems on the final. EMAG 1 here. Because some people transfer in here, and they literally never have EMAG 1 here. They have it somewhere else, and we don't know if they're really going. But I'll do that on Wednesday, buddy.
Okay.
Maybe I'll give you a few problems that you should understand what the later that I do. I just